So when we introduced linear momentum, one of the things we did was we came back to Newton's second law and showed how what Newton's laws are really trying to do is give us a way to keep track of the linear momentum of a system. Well, the same thing's true when we think about angular momentum. What we'll see here in a second is that the rotational version of Newton's laws, what they're doing is they're giving us a way to keep track of the angular momentum of a system. So if we think about the translational version first, so F net equals ma. On average, I can think of the average net force as just the mass times the average acceleration, and of course the average acceleration is nothing more than delta v over delta t. But of course I can take this mass term and tuck it back inside, and then I've got delta mv, and that's just p, the linear momentum. And so the net average force acting on my system is telling me how the linear momentum of the system is changing with respect to time. So if the vector sum of the forces acting on the object is 0, the linear momentum of the object doesn't change. Instead, the linear momentum is constant. The rotational version of Newton's second law I can play the same game with. So what I'm going to do is just say, well, on average, the average net torque acting on my object, that's got to be equal to the rotational inertia of the object times its average angular acceleration. And again, the angular acceleration, average angular acceleration, is equal to the change in the angular velocity divided by time. I can take this moment of inertia, tuck it back inside, and then I've got the change in I times omega, and that is the angular momentum. So what I see here is that the average net torque is equal to the change of the angular momentum of my system with respect to time. So if the vector sum of the torques acting on my object is 0, then the angular momentum of my object is constant, and again it doesn't change. One of the things we talked about is that of course I can rearrange this equation, and when I rearranged this equation and solved it for delta p, it basically gave me the impulse momentum theorem that told me that the change in the linear momentum of an object is equal to that average net force acting on the object times however long it acts, and we said that defines what we're going to call the net impulse. So the net force acting on my object over time, that tells me what the net impulse exerted on my object is, and that's going to equal the change in the object's linear momentum. Well, I can take my rotational version of Newton's second law and again solve that for delta L. So if I solve this equation for the change in the angular momentum, what I get is that's equal to the average net torque acting on my object times, again, delta t. And so what that means is that we can define something called the net angular impulse. The net angular impulse exerted on an object is going to be equal to the average net torque times how long that torque acts on the object, and that's also going to be equal to the change in the object's angular momentum. So thinking in terms of a system now, if I say, well, the change in momentum of my system is going to be equal to the net force acting on my system, again, times however long I let it act. And again, I can break up that net force into forces that are internal to my system and forces that are external to my system. Newton's third law tells me that these internal forces are going to cancel, and so I'm left with that the change in momentum for my system is equal to the net external force acting on my system times some chunk in time that I let those forces act. This equation, of course, gives me a way to recognize when the momentum of my system will be conserved. It'll be conserved when the net external impulse acting on my system is 0. So either the net external force is 0, or again we make delta t negligibly small so there's no time for that force to act even if it exists. We can think about the same idea with the rotational version of Newton's second law. So take our equation in terms of delta L and now just think about that equation as it relates to a system of things that rotate. Again, what that's going to tell me is that the net torque acting on my system times however long I let it act, that's going to change the angular momentum of my system. And again, I can break up that net torque term into thinking about internal torques and external torques. And the internal torques, again, are going to cancel out. So what that means is that if you want to think about how the angular momentum of a system of rotating objects is changing, what you need to think about is the net external torque acting on the system times some chunk of time that you let them act. So again, for a system of objects, the angular impulse exerted on the system by external torques is going to tell you how that angular momentum changes. And if that net external impulse is zero, then the angular momentum of your system will be conserved. And so you can get an angular impulse to be zero by either saying that the net external torque acting on the system is zero, or even if there is some non-zero net external torque, we make the time it's allowed to act really, really small, so there's no time for that external torque to act to change the momentum of the system. So this, of course, leads us to the idea of conservation of angular momentum.